All right, good day, students. We are going to continue talking about momentum today. We've pretty much wrapped up the center mass part, so now we go into momentum. And to start with, there is something different between a Mack truck moving at 20 miles per hour and roller skate moving at 20 miles per hour. Okay, obviously, if you stepped in front of one of those, if you had a choice to step in front of one of those, you'd probably choose the roller skate because you realize it will do less damage to you. So there's definitely something different about them, and they're different because they have different momenta. Okay, the momentum of an object, we're using a letter P. We're kind of out of some other letters. We used M for mass, so we can't use M for momentum. So most textbooks will use a P. Momentum is a vector, so we're back into a vector world here. And the direction of the momentum is the same as the direction of the velocity. And it turns out that the momentum of an object is its mass times its velocity. Okay, so since velocity is a vector, right? Momentum's a vector. This is a scalar, it just scales the size. So again, momentum and velocity will always point in the same directions. And because direction is important here, even if a baseball came in at, let's say, 20 miles or 20 meters per second and it hits a bat, and it leaves at 20 meters per second, let's suppose it was the exact opposite direction that the baseball left. It might be tempting to just say, well, the momentum hasn't changed, but it has because the direction has changed. The momentum was this way, and then it's that way. So even if the speed doesn't change, if the velocity changes, that means that there was a change in momentum, and that becomes a physically meaningful thing for us, as we will see. Okay, it turns out that to change the momentum of an object, you'll need to apply a force for a certain period of time. And so this is what we call our impulse relationship. And the impulse relationship says, hey, if you take the average amount of force that you're applying over a period of delta t, okay, if you apply that force over a period of time delta t, you will change the momentum of the object according to this relationship, m times delta v. Okay, now that's, again, we're assuming rigid masses. We're not assuming masses that change. So we're dealing with things like rocks, cars, things that either change mass so slowly that it's not important, or that don't have any mass change. Okay, so this relationship is called our impulse relationship. Many books will go on and just define J as your impulse. Again, we're running out of variables to use and so forth. Instead of using I, they actually use J for impulse. Okay, that's what J stands for. And basically your impulse is simply a change in momentum. Okay, so if the momentum of an object changes, however big that momentum changes, that's called the impulse. And then if we take the impulse and divide by the amount of time that it took for that impulse, that will end up giving us our average force. Okay, so these relationships on this page are very important. Again, the things that we're learning, probably you've understood these concepts from your mind has figured out general rules about how nature works, but you may not have realized what it was called before or why it was that way. But if you imagine, getting hit in the face with a boxing glove here, say you're a boxer, and the punch is coming and you kind of juke your head backwards here, right, as the punch lands, then you're going to extend the time of the collision, right? The glove is going to be in contact with your face for a larger period of time, and what that does, if it's going to change the momentum of your head, but we do that over a longer time, we end up having less force involved. Okay, in other words, this punch won't land and it'll, as they say there, poof, it doesn't do as much damage to the boxer. On the other hand, if your head was juking towards the punch and the punch lands and this whole collision is over in a very short period of time, then we will have very large forces involved and it will do more damage. So again, you're familiar with this idea. In the next couple slides will help reinforce the fact that you're already aware of this, I think. So let's suppose we have a truck driving along and it's got a certain momentum mv. Okay, we can stop the truck by having it, let's say, wreck into a bale of hay right here, or we can have it stop, as the momentum mv, and we can have the momentum go to zero by hitting a very rigid wall. Well, again, hitting the bale of hay, we are going to slow the truck down and stop it over a fairly long period of time, and that means small forces involved. Okay, kind of cushions the blow, if you will. On the other hand, if we slow the truck down over a very short period of time here, right, if t is very small, then we end up with very large forces involved, which of course do lots of damage. Okay, so again, if you imagine taking your fist and slamming it into a brick wall, you'll know that you'd expect to break bones in your hand or injure your hand pretty severely, right? You wouldn't do that. And the reason for that is because your fist would have certain momentum as it hits the brick wall, and it would end up stopped very quickly. So quick stops mean big forces involved, okay? On the other hand, if you were to put a big pillow, a couple big pillows on top of the brick wall and then punch them, it doesn't hurt your hand, because as your hand hits the pillow gives, it compresses, it compacts, and your fist keeps moving. And so you've extended the time over which you're stopping your fist, and because the time's larger, the forces involved are much, much smaller. Okay? Hopefully that's making sense. Okay, here we see some pictures. Here we see we're going to see a series of pictures here that shows some high-speed photographs in some of these sporting situations you're familiar with. So here's a tennis ball hitting a tennis racket, and the picture's captured at that moment where we have a lot of force involved. And you can see, you know, our eyes don't actually respond very quickly. Our mind and our eye can only process about 15 images per second. So that's the reason that movies and TV and videos displayed on your computer screen, that's the reason they look like they're fluid motion. You know, if you had a blinking light, if it was blinking at less than 15 times a second, you'd be able to tell it was blinking. But if the blinking goes up to, let's say, 30 times a second, the light was blinking, your brain would see it as just the light's constantly on. And so, you know, anything that's happening over a short period of time, a very short period of time, your brain is going to miss. And so we don't really, you know, in the case of watching a tennis ball hit a tennis racket, we generally don't see this. You know, we do not see this. Let me see if I can get a better color for the, no, that's not working. Why is it not working? I'm trying to do white. I guess it's not writing on there. Anyway, hopefully you see what I wrote. That's not working very well. I don't know how to get a good color on this thing to show it up. No, there. Anyway, the tennis ball hitting the tennis racket here in a very short period of time, there's very large forces involved. It doesn't mean that the overall force over a period of time was huge, but at least this moment in time, imagine how much force it would take to compress a tennis ball to look like that. There's tremendous forces involved. We see the same sort of thing in racquetball. Here's a picture of a racquetball. Again, I don't know how well my markers show up here. Okay, yeah. So the racquetball is hitting the wall, and this is over a course of a very short period of time. You know, 1.93 milliseconds, that's 2 milliseconds or 2 thousandths of a second. You know, and over here we're at 1.34. So from here to here, we're talking about a half of a millisecond, or, you know, maybe like 1/5000th of a second approximately. And so this is happening very quickly. So your eye does not catch it if you play racquetball. But when the racquetball hits the wall pretty hard and makes that sound that it's, you know, classic sound that the racquetball makes when it hits the wall, the ball is doing something about like that. And if you've ever squeezed a racquetball, you know that would take a tremendous amount of force to make that happen. Okay. Same thing with playing baseball or softball. Here we see it looks like a softball hitting a bat. And again, look at the deformation here. Look at the deformation in the ball here, and the bat. You know, we really don't know if the bat's flexed. I mean, the bat's much harder than the ball, so it's probably mostly the ball flexing here. But of course, the bat itself would be compressing a little bit there as well. But that would take tremendous amount of force if you were to try to just push on a softball to make that happen. That would take a tremendous amount of force. And so during the collision, right, the collision's brief, right, as it shows right here, the collision is brief. And that means that the ball experiences a force that varies during the collision and changes the momentum of the ball. Now, if we were to graph that collision force, what we would find is that it varies, right? The amount of force at a particular time will vary. In other words, if we were to graph, if this was the time of maximum compression, the ball, you know, would be, you know, if we graphed force versus time, you know, what we would find is that, you know, the force is very large perhaps at one moment, but overall the force the force is averaging something smaller than that. So when we look at thousands of pounds of forces on a baseball bat, when a baseball hits a baseball bat in professional baseball, sometimes the bat even breaks, right? That bat, that rigid maple or ash bat, will actually just break in half, and that's because at certain moments in the swing, the force is very large, and if it's along the wrong direction on the grain of the wood and so forth, the forces, it can cause the bat to just break and shatter. So the forces are very large, but again, that doesn't mean a professional baseball player, because there's thousands of pounds of force involved when the ball hits their bat, doesn't mean they can hold a car up on the end of their bat. They're not that strong. The thing is, that force is only happening for a very, very short period of time. Okay, so it's almost like an instantaneous type of big force. So if we were to look at a graph, what's happening is, again, the ball's starting to hit the bat here, and then it compresses, compresses, compresses. Then we're up at this big force just for a fairly short period of time, and then the ball turns around and starts changing its direction of motion, and it comes off the bat here. And so, looking at a real collision process, we get curves like this. Usually what we'll do, if it's a very short period collision, most of the time we'll just say, well, what was the average force acting over that period of time, delta t? And that's how we would calculate it. But just like the formula on the previous page showed, that if you want the impulse, the change in momentum, you would integrate over f of t dt. In other words, you would have to take this curve, and you would integrate and find the area under this curve and add all that up, and that's going to be your impulse, right? Which is your mass times your change in velocity. Again, the other alternative, which we'll use a lot of times in our problems, is to just say, well, what would be the average force over that period of time? And if I have the average force correct and I estimate the time of the collision properly, then this area that I'm shading in here would be exactly equal to the area under the real curve. And so we get an approximation as to the force. But keep in mind, the peak force, it's not uncommon for the peak force to be 2 or 3 times larger than that average force. Okay, so hopefully that makes sense. Another example I like to give, it's a game some of you may have played before, sometimes played at picnics, summer picnics, or family reunions, or maybe at orientations at college or whatever, I don't know. But the idea is you have a partner and you toss a raw egg to them. You start just a couple feet apart and you toss a raw egg to them and they catch it. And if your egg survives, then your team, you each take like a step back, and then they toss the egg back to you and you catch it. And if the egg survives, you both take a step back. And you have teams, of 2 people doing this, tossing an egg back and forth, raw egg, until there's one team left. And you see who can catch the egg, throw the egg and catch it furthest apart. Well, usually the people that are out of that game really quickly are the ones saying, hey, Billy Bob, throw me the egg, and they're holding their hand nice and rigid here. They're not going to flex their arm at all, and the egg comes flying in, and they stop the egg in a very, very short period of time. And when they stop in a short period of time, it means there's big forces involved, and guess what happens? The egg breaks. Okay, the people that generally win that contest are what we would say people with soft hands. When they catch the egg, as the egg comes in here, they move their hand like this, kind of with the motion of the egg, and they take they slow the egg down over a longer period of time. And so while they're changing the momentum, the same as the person that broke the egg, they're doing it with a long time, which means small forces involved. And small forces involved means hopefully the egg survives. So another example of this idea of momentum change and impulse. Keep in mind that then we can extrapolate this to things like car crashes, right? Because if you think of your head and your brain as kind of like the egg, then you can see why in a car crash we actually want the time of the collision to be as large as possible. People tend to wonder why cars are built collapsible and to crunch up. That's why. The longer we can make the collision process last, the less force is on you and your internal organs. It's usually not the external injuries like the lacerations or cuts from the glass and things like that, or bruises externally that kill a person in a car crash. If they have a fatal injury, oftentimes it's because of damage to an internal organ like the brain, the heart, the liver. Our internal organs are soft and squishy, right? We are not creatures that could unzip our chest and take out our organs and so forth. But if we could, if we could unzip our chest and pull out our heart and say, hey, look, here's my heart, we would never throw it against a hard wall, because we'd know, oh, that might ruin it. It might hit the wall and get ruptured or whatever. We want to keep those things in there safe. And so by slowing our body down in too quick a period of time, like in those old-fashioned cars, if they hit a telephone pole and didn't collapse, then the person that's buckled in there, for example, their heart, their brain, their liver, everything inside of their body is stopping very quickly. And we know that if we stop things very quickly, we end up with big forces involved, which is not good on our internal organs. And so it's oftentimes the internal injuries that lead to the worst situations in car crashes. And so here we see that. Sometimes people think, oh, those old-fashioned 57 Chevys, you could hit a brick wall with them and they wouldn't even get scratched. They were much better cars or safer in one of those. Well, in terms of safety, we'll talk more about that, but the idea is, if you drove a 57 Chevy into a brick wall and it didn't collapse, you've got huge forces and you're probably going to burst your aorta or, some kind of horrible internal injury, and you could end up dying. And so the old-fashioned cars, they held up well, but in a collision like this, what was happening was the car was being taken and somebody could still use the car, but the person was dead. What we want is the opposite. Cars can be replaced. So modern day cars are designed much lighter and they're designed to collapse. The engine, folds up over the metal breaks, there's stress points where the metal can break, glass can break, so forth, so that the time of the collision, by collapsing, you extend the time of the collision, which decreases the amount of forces on the person in the car. And so nowadays we drag the car off and that's gotten rid of and the person survives. They get up and walk out of the crash. And you've probably seen this. You've probably seen some fairly horrific looking crashes in modern day cars and people were sitting alongside the road and they're okay. And that's just tremendous. That's a miracle of modern engineering to have learned, understood this process. Okay? So the most important factor in terms of reducing forces in a collision is the collision time. That is the time it takes for the person to come to rest. So we want to extend that. And so we do that by having the car built in a way that it collapses and crunches up really well. We also do that with things like innovative ideas like airbags, so that if you hit something and your motion of your car stops, it changes very quickly. Within a very small fraction of time, this airbag blows up and provides now a cushion for your head and chest to hit against instead of the steering column. The steering column and the steering wheel for a driver ends up causing a lot of serious injuries, but if you have that airbag there, that helps to extend the time of the collision, and by extending the time of the collision, by stretching that process out of stopping the person, we decrease the force. And so airbags are another extension of this idea, and they've been highly successful. Now, if we were in class together, I have a little demo that I could show you that would help make this point clear. Unfortunately, I'm at home and I do not have that demo, and it's kind of a touchy demo. It has to be just the right mass thing set up the right way to make the point, to make the point for it to work right. So unfortunately, I can't do that for you, but let me just address the idea of bouncing versus sticking, because sometimes students think, well, why don't we just design cars with big rubber bumpers around them, almost like at the amusement park you ride the bumper cars. Why don't we just make cars that we drive down the road with these big bumpers, and then when we have collisions we just bounce off each other and laugh, and nobody's car's damaged and everybody's fine. Well, there's a couple problems with that. First of all, one thing that's concerned is if you were to bounce and not stop, you're liable to go a direction, bounce off something or somebody, and you're still moving, which means you're probably not going to have just one collision. You're going to be bouncing around for a while. That's one thing. You're going to cause disruption all over the place, and probably multiple people, or just like in the bumper car situation, we're going to have a big issue. That's one problem. Now, the bigger problem, though, is that bouncing generally produces bigger forces than just sticking. Okay, if I take a car and it has a momentum mv, right? So this car has a momentum mv towards the wall. Again, if the car doesn't collapse, or if the car collapses, okay, then what I'm doing is I'm taking the momentum from mv to 0, right? Because of the velocity, if the car stopped, then the momentum goes from some amount mv down to 0, right? And so I'm changing the momentum by an amount this size. And if I do it over a period of time t, accounting for some collapsing, I end up with this amount of force involved. Now, if the car bounces, okay, if the car bounces, then we're not going from MV to 0. We are ending up going from MV to minus MV. In other words, this car has momentum. If it bounces off the wall, it has momentum going the other direction here, right? And so we end up going to minus MV, and going from MV to minus MV, we've pretty much got twice the momentum change, or twice the impulse. So we have a bigger impulse in this situation, and if the time of the collision is somewhat similar, which it usually is, then we have bigger forces involved. So bouncing actually puts a bigger force, generally speaking, bouncing puts a bigger force than sticking. Okay, so the best thing you could have happen in a car crash is for your car to hit, crunch, and stop. Okay, that's what we want. We want your car hitting, crunching, and stopping. And so cars are set up today to do that. Okay, bouncing, not good. Bouncing puts a bigger force. This is actually one of the reasons people that do karate, if you've ever seen somebody do karate, and break a board or something with their hands, they learn how to take their fist, and I don't know how to draw a fist there, but something like that. They throw their fist down, and usually they'll do it in such a way that it kind of bounces off the board. And by a bouncing type blow, you actually increase the force. All right, a bouncing blow actually increases the force. It's one of the reasons those quick jabs in a boxing match, sometimes you'll see some quick jabs and a person's head kind of bounces backwards. Those quick bouncing type of blows to the head in a boxing match tend to do a lot of damage. And so again, karate experts are trained to, they learn how to kind of do a bouncing type of a blow, and it actually increases the amount of force involved and breaks the board. So again, cars, we do not want them with big bumpers and bouncing going on. Okay, so let's take a look at a sample problem here with momentum change. Let's get some more mathematics going on now. And let's look at a race car collision with a wall. This happens quite a bit in racing. And the NASCAR race cars, I think there was just a fairly horrific crash recently, but one of the famous ones that people talk about because it was a fatal collision was when Dale Earnhardt Sr. Died at Daytona. If you watch the video of that, I mean, his car hits the wall, and it doesn't seem like it was that bad of a collision, but the thing is, he's hitting a very rigid wall. And so when you hit a rigid wall and your velocity changes rapidly in a very short period of time, there's huge forces involved. And so here's an example. It says, let's take an overhead view of the path taken by a race car driver as his car collides with a racetrack wall. Just before the collision, he's traveling at a speed of V initial equals 70 meters per second. Pretty reasonable. I mean, they're definitely going over 100 miles per hour. We know that. And they're along a straight line at 30 degrees from the wall. Just after the collision, they're traveling at a speed of 50 meters per second along a straight line at 10 degrees from the wall. So their speed has slowed down, but really not too much, maybe from like 150 to 100 or something like that. And the question is, what was the impulse on the driver due to the collision? Okay, so we want to know the momentum change for this driver. So what we need is the momentum before the collision, and then we need the momentum after the collision. Okay, and so this momentum change, P final to P initial, right? This momentum change like that, or actually it's the other way around, from initial to final, that momentum change is going to be equal to the average force times the time of the collision, right? That's going to be equal to our impulse, right? Our momentum change. And so we want to go ahead and figure that out. So when we look at this, the change in momentum would be mv final minus mv initial, or in other words, if the mass of the car doesn't change, which we'll assume here that the car stays intact, then it's just the mass of the car times the change in velocity of the car. So we've got to get the velocity of the car, and we'll do this along each dimension. Much like our strategy is for solving a lot of two-dimensional problems, we're going to break it into an x part and a y part. So looking at the x part of the momentum here, the x change in momentum would be the mass times the change in the x velocity, and the x velocity before the crash would be 50 meters per second times cosine of 10 degrees. The final velocity would be the momentum vector here. The working angle is 10 degrees right there, and so we would take our 50 meters per second after the collision times cosine 10 degrees. That gives me my x component of my final momentum. Okay, the x component of the initial momentum here would be the original velocity times, or the velocity x component initial would be the magnitude of the velocity times the cosine of the angle there, and that's of course a 30-degree working angle. So we do that calculation, run through that in our calculator, and we find out that the x momentum change, or the x impulse, is minus 910 kilogram meters per second. In other words, the momentum change in the x direction is that way, which makes sense. You know, the car was initially kind of going left to right, hit the wall. We expect the wall to kind of slow it down some, and so there's a momentum change back that direction. Okay. Then we look at the momentum change, the impulse in the y direction. So we take the mass times the change in the y velocity. Well, the y velocity, in the case of the final y velocity, if the car is going down at an angle like this, then the y velocity is going to be down like this. It's going to be a negative component. And that negative component would be the size of the velocity, right, 50 meters per second, times the sine of that angle, working angle. And of course it's negative. So we have our x component, or our y component of our final velocity. We subtract off the y component of our initial velocity, and the initial velocity was going to have a positive y component here, and it would be equal to the 70 meters per second times the sine of 30 degrees, the initial angle, working angle. And so we can crank through that, and we find out that the y momentum change, or the y impulse, is negative 3,495 kilogram meters per second. Notice that there is no special name for this unit. You know, when we're dealing with momentums, you know, a momentum or a momentum change, mass times velocity would be in units of kilograms meters per second. There is no special name for that unit, and so we usually just say kilogram meters per second. A lot of times you'll catch me just saying units. You know, since that's the unit for momentum, you know, I might say J sub y is minus 3,495 units. And I tend to use that terminology a good bit because rather than having to say out kilogram meters per second, which is kind of, you know, takes a little longer to say and it draws it out, I just refer to this as a unit of momentum. Okay, so if you like that little trick, you can do that. Anyway, continuing on with this problem. In this particular case, we've now got the x and y components of the momentum. So again, if we want to get the, or the x and y components of the impulse, change in momentum. So if I want to get the entire impulse in vector form, I mean, here it is in component form, right? But if I want to get the magnitude direction form, I would take the square root of the sum of the components squared. So I'd square both these, add them together, take the square root, as I show right here. And we end up with a total momentum change, or total impulse, of 3,611 units of momentum change. The angle at which that momentum change occurs, we can take the inverse tangent of the size of the y component over the size of the x component. So notice I'm not putting any signs in here. It's just 3495 over 910. We take the inverse tangent of that, and that's going to give us our working angle. So when we look at our impulse, we know we had a negative, you know, y impulse, we had a negative x impulse, and so obviously our impulse vector points like this, right? And so the angle we just figured out is this one. It's always the working angle, right? And so in other words, I would describe that as 75.4 degrees south of west, right? Or in polar coordinate form, you would say, oh, it's 225.4 degrees or negative 104.6 degrees. Remember, mathematicians like to take their angles and come up off the x-axis like that. Or if you know, sometimes I don't know that it's considered proper, but you can do a negative angle like that clockwise off the x-axis. But either way, we've got our momentum size here, and we've got the angle. Okay, so we've now got the momentum change, or the impulse, in magnitude direction form. Now, if we knew how long the collision lasted, so for example, in this case, if they told us the collision lasted 14 milliseconds, then we could figure out how big the average force was on the driver, right? If the impulse on the driver is 3,611 units, and we divide that by 0.014 seconds, which is 14 milliseconds, right? If we do that calculation, we find out that the force on the driver is 2.579 times 10 to the 5th newtons, or 257,900 newtons. Okay, if we assume a fairly average sized person, 80 kilograms as the mass of the driver, what that means that the acceleration on the driver in this case would be about, 329 G's, or about 3.22 times 10 to the third newtons. We divide that by their mass. I guess this would, wait a minute, I guess that would be in meters per second squared there. I'm not sure why that says newtons. If I did this calculation right, if I took this and divided by 80, which it looks like I did, the units for acceleration should be meters per second squared. So scratch out that newtons there, that's a meters per second squared. And then if we divide this by g, this number by g, that would tell us how many g's of force were involved, and we get 329 g's, and that's a problem. The human body can withstand up to about 10 g's or something like that. And so unfortunately, in this case, this would be a fatal accident for the driver. So you can see that even a glancing type collision in a race car off a very rigid wall can lead to some big problems with the forces involved on the driver. Okay, so we're going to do an exercise here. I would have done this as an in-class graded exercise, but since we're doing this on video, I would just encourage you to, after we read the question here, to pause the video and try to work this answer out for yourself, and then run the video again to see how you did. It says a football of mass m, initially at rest, is kicked so that it leaves the foot at a speed of v. If t represents the duration of the collision between the ball and the foot, which one of the following expressions determines the magnitude of the average force exerted on the ball? Okay, so we've been talking a lot about this. You might need to go back in your notes a little bit. Hopefully you have the lecture notes printed out or available in front of you. I've been posting the lecture notes in the archived lectures folder if you didn't take note of that. So you can still get the slides printed out or available as you go along in these videos. But anyway, one of these answers down here at the bottom is the correct answer. And again, it should be the force, the average force exerted on the football. So again, we have the football. Here's the laces on the football, and Charlie Brown comes and kicks the football, and this time Lucy lets him kick it. So it starts from 0, it ends up at some speed v, okay, and we want to know, and football has a mass m, and the time involved is t. So what was the average force that Charlie Brown's foot here, put on the football? So pause the video. Okay, so hopefully you identified mv over t as being the right answer. Again, momentum change, the impulse is equal to m times the change in velocity, right? And then that's also equal to the average force times the time of the collision. So in this particular case, the final speed was v, the original speed was 0, so there's our momentum change. Right? Well, it's a velocity, but again, we'll just assume the football is going to the right in the positive direction. Okay, and that would equal the average force, right? The average force times the change in time, which is t final, which is t minus the original reading on our stopwatch would have been 0. So we end up with mv equals the average force times the time, or in other words, the average force is going to be mv over t. Okay, so hopefully you work that out. Some of these probably don't even have the right units. If you, I don't know, if you go through some of these, I don't know if they're in the right units or not. Well, yeah, certainly not, because mv times t would not be the right units. Our units for force should be mv over t, or kilogram meters per second, right, or kilogram meters per second squared, which is the mass times acceleration. So these aren't even in the right units, some of these. Okay, so hopefully you determine the right answer. If not, again, go back and think about what I did there and see if you can convince yourselves that the right answer is D. Now, one other thing before we wrap up for today, and again, you'll have to practice this idea of momentum outside of class. The more problems you do, the more problems you ask about during our Zoom lectures, the more effort you put into this, the better it'll make sense. And again, the rules haven't changed. Even though we've gone to virtual lectures, you should still be spending a couple hours each day on just this course. And so if you watch this video, you still should be putting in plenty of extra time over the next few days at practicing it, reading your book, trying problems, reading solutions to problems, getting help online with video things that are available. Remember, your e-text that's up in WebAssign has some little video clips and tutorial type things and demonstration videos. Definitely try to make use of whatever you can to help learn this and understand it. Our period of time together in these little lecture videos is short, So I'm hoping that the Zoom lectures where I help answer your questions about the problem solving are helpful to you. Anyway, so let's wrap this thing up for today. It says the time rate of change of momentum of a particle is equal to the net force acting on the particle and is in the direction of that force. So this expression right here is exactly how Isaac Newton wrote his second law of motion when he published his work. Okay, so this is the second law of motion. Now, we didn't really look at it in that form when we first learned it in class. And the reason for that is because typically we write the second law of motion. Most of you probably have learned it, and most of the time we use it in this format, F equals ma. Okay, that's the second law of motion in our universe. Okay, if something has a net force, the net force is equal to the mass times the acceleration of that force, or of that mass. So F equals ma. Now that's the assumption. Okay, this works if we assume this is constant. If the mass of the object is not changing, then this F equals ma, this version of the second law works. Okay. On the other hand, what if we have a varying mass? What if the mass of the object is changing as we go as well? It turns out that then this rule over here will not work out for us. Okay. If the mass is changing, what we're going to need to use is the original expression here, which is that the net force on an object is equal to its time rate of change of its momentum vector. Okay, and so using our calculus, if we know momentum is mv, and we take the derivative of that with respect to time, you'll notice that if mass stays constant, right, if mass stays constant, we can bring that out front, and then we're just taking the derivative of velocity with respect to time, which ends up being equal to acceleration. So you can see that this works out to be F equals ma when the mass is constant. If the mass is not constant, then we have to do dm dt, right? dm dt times the velocity plus the mass times dv dt. So we got an extra term in there when we go to differentiate this with respect to mv, where both m and v can change. And we'll talk more about that in the next lecture. But for right now, just recognize that this is the original form that Isaac Newton wrote his second law of motion in. And it works, most of the time works like this, but if we have a changing mass, we're going to need to do a little bit of additional work and understand that, and we'll get to that in our next lecture session. So have a great day, keep working hard. We have a test coming up before long, so we're liable to ease off a little on these lectures and focus on getting ready for our test as the week progresses here.